Hello everyone, welcome back to Explore Electronics. In this video, let's see the next concept of Opamp, that is integrator and differentiator. In the previous video, we have seen Opamp inverting amplifier and Opamp non-inverting amplifier. So let us look into the integrator now. So Opamp integrator is the thing we are going to look at. So first let me write the circuit. Here we have an Opamp with inverting and non-inverting terminals like this. So Opamp integrator will be having a resistor connected to the inverting terminal, and the feedback path will be having a capacitor. Capacitor is connected as a feedback device. So this capacitor will be act as a feedback network now. So let me call this as C and this as R, and here we are going to give the input. Let me call it as Vi, and usually the non-inverting terminal need to be grounded, and V0 we are going to measure over here. This is V0 with respect to ground. Here also Vi we are going to apply over here with respect to ground. So let us derive the expression for V0. Okay, so first we need to take the input currents. Here the current flowing through the resistor, let me call it as I1, and current flowing through the capacitor, let me call it as IC, and this point I am going to name it as A, and we know that voltage at this point means VA will be equal to 0. Why? Because the non-inverting terminal is grounded. Because of this connected to 0 volts, because of the virtual ground concept we can take the point at A or the point at the inverting terminal will be having the same voltage of the non-inverting terminal. That's why point A will be having the voltage 0. And now let me take the currents now. Current flowing through the, first let me take current flowing through the resistor R. It is I1. I1 can be written as, here it is Vi and this point is Va. So let me take the voltages across that resistor as Vi minus Va divided by the resistor value, that is R. Here what is Va? Va will be 0. That's why the current expression becomes Vi divided by R. Let me call it as equation 1. Now let me take the current through the capacitor. Capacitor means that is the feedback network. Through the capacitor the current is flowing is If, and we know that the current flowing through the capacitor will be C into D into the voltage Va. The voltage across the capacitor will be measured from this point to this point. So here it is Va, here it is V0. So it is Va minus V0 with respect to dt. C into dV minus dt. That is the expression for current through the capacitor. Here also if we take this Va is 0, what happens? C into dV naught divided by dt will be the expression for If. So we need to carry this minus. Va becomes 0 here. So this is the expression for current through the capacitor. And we know that the current flowing into the Opamp will be 0 always because of the input resistance Rin of the Opamp is infinite. So there is no current absorbed by the Opamp. That's why current into the Opamp is 0. Whatever the current flowing through the resistor will flow through the capacitor. So let me take it as If. So I1 is equal to If. So If, we know that If will be equal to I1. So it is minus C into dV0 divided by dt is equal to Vi divided by R. So let me take this C to right side with minus sign. So it is dV0 divided by dt will be equal to minus 1 by RC into Vi. Now if you are going to integrate on both sides, what happens? Here in the left hand side we have dV0 by dt that get cancelled with the integration, so we left with V0. So the left side expression will be V0, At the right side we are integrating. As it is, I am going to write minus 1 by RC into VI into dt. Here 1 divided by RC is constant, so minus 1 divided by RC, we can take it out. Within the integral we have VI with respect to dt. This is the expression for V0 now. Here you can observe there is an integration symbol. We are taking the integration of VI and we will be having 1 divided by RC as a coefficient. So this is what the expression for the output of an Opamp integrator. And now if you look at the waveform, if we are going to apply a square wave like this to this integrator, what we are going to get as output? We are going to get, let me take this as Vi with respect to t, and we are going to get the output as this. This is the kind of output we are going to get for a integrator. So then let us move on to the differentiator. So the next thing is Opamp Differentiator. So in the Opamp Differentiator circuit, we have an Opamp with two terminals like this, and in the place of resistor now we will be having a capacitor. In the previous circuit we have seen the capacitor will be at the feedback path, that will be integrator. Now the capacitor will be at the inverting terminal, and we are going to apply Vi over here by grounding this positive terminal of the Opamp, that is non-inverting terminal, and usually RF, that is R, will be the feedback resistor, and here is our output V0. And now again we need to take the currents. Current flowing through this, let me call it as I1 again. This current will not flow into the Opamp, it is 0. So the whatever the current flowing through the capacitor will flow through RF fully, let me call it as IF. Now this point is again A. If you take the voltage at point A will be 0 because of virtual ground. The non-inverting terminal is grounded. That's why this point voltage also same as this, 0. Now let me take the currents first. Current I1, that is the current flowing through the capacitor. I1 can be written as, how we are going to write I1? C into dV by dt. Here the voltage across the capacitor Vc can be written as Vi d into Vi minus Va divided by dt. Here what is Va? Va is 0. So C into dVi divided by dt is the expression we are going to get for current I1. Similarly, we need to take the current flowing through the RF. Current through the resistor RF can be written as IF is the current flowing through the resistor, is equal to voltage across the resistor RF is Va minus V0 divided by RF. Right? Here again Va can be taken as 0. It becomes minus V0 divided by RF. And we know that the currents are equal. So we know that IF will be equal to I1. Let me take IF. This is my IF. Let me take V0 divided minus V0 divided by RF over here. What is I1? I1 is C into dVi divided by dt. So C into d into Vi divided by dt. Now we need to get the expression for V0. So let us write the expression for V0 by taking this RF to right side with minus sign. It becomes minus RF into C into dVi divided by dt. Now this is the expression for V0 we are going to get. This minus sign indicates we are applying input to the inverting terminal. That's why we are going to get the minus sign. And here again, if you look at the input and output waves, again if we are going to apply a square wave like this to the input side, we are going to get the differentiator output like this. So this is the differentiator output. Like this we are going to get the peaks and then it will be get reduced. This is the output of the differentiator. Okay. So far we have seen inverting amplifier, non-inverting amplifier, integrator and differentiator. So in the next video, let us see Opamp difference amplifier and Opamp summer. Summer, that is the Opamp adder, and also the op-amp subtractor we will see in the next video. Thank you.